Welcome to Chapter 3 and Section 3.1. In this chapter, we're going to be looking at some uses of derivatives. We're going to be looking at some properties, how they relate to graphs and functions. And we're going to look at some new concepts, including the idea of maximum and minimum values. So in Section 3.1, we're looking at the first derivative and the behavior of functions. So a function is said to be increasing on an interval from A to B if the graph rises on the interval. So if we're thinking about tangent lines that could be drawn between A and B, if we picked some points out here just at random on graphs like this, and we draw the tangent lines, you can see that the slopes of all of these lines are going to be positive. Okay, so a function is increasing on an interval if the graph rises as we move from left to right. So the tangent lines will have positive slopes, meaning that the derivative will be positive, right? Because the derivative is the slope of the tangent line. On the flip side of this, we say that a function is decreasing on an interval AB if the graph falls on the interval. So again, similarly, if we just pick some random sample points here and we draw tangent lines, you can see the slopes of these tangent lines would, of course, be negative. So that means we would have a negative derivative that corresponds to our decreasing function. So we draw our conclusions down here. We say that f of x is increasing on the interval from A to B if and only if f prime of x is greater than 0. So if our derivative is positive, that means that f of x is increasing on that interval. F of x is decreasing on the interval if and only if f prime of x is less than 0. And we say that f of x is constant on the interval if and only if f prime of x equals 0. So if the derivative is 0, the slope of the tangent is 0, that means that the graph is perfectly horizontal. It's perfectly flat, right? Because a horizontal line has a slope of 0. So that would give us a constant function if we had something like that. So let's take a look at an example with a graph here. Determine any intervals of increasing and decreasing for the given function n of t. So I'm going to have our increasing and our decreasing here. So for our increasing, when you're given a graph like this, it's pretty easy to identify. You're just looking for where the graph is going up and going down. So it starts off going up, and I'm going to approximate that changes at about 2. And then it's going down until around 5, going up until about 7. It flattens off until 8, then it goes down until 9, and then back up again to 10. So for increasing, that's going to be here to here, here, and here. So that's going to be 0 to 2, 5 to 7, and 9 to 10. Remember, these are intervals, not points. and then decreasing there and there. So we get from 2 to 5, along with 8 to 9. And then we have that one little piece left over where the graph wasn't going up or going down. So it would be constant on this portion of the interval. So from 7 to 8. All right, so when we're looking at the graph itself, it's not too hard to identify where it's going up and going down. What we need to be able to determine is what is a graph doing based off of the function, like the formula, okay, the algebraic equation that we have for it. So that's what we're going to talk about next. So if a function f of x is defined at x equals c, and either f prime of c equals 0 or f prime of c is undefined, then the number c is called a critical value of f of x. And the point c comma f of c is called a critical point. Okay, so if we have some value on the function where the derivative is 0 or possibly undefined, that's a little more rare of a case, but it does happen. This value is called a critical value, and the point where it occurs is called a critical point. So now, if we want to use this idea to determine where a function is increasing or decreasing, here's what we're going to do. So we're going to first find any critical values of the function. Okay, so we're going to find any values where the derivative is 0 or undefined. We're going to draw a number line and label the critical values. And then on each of these intervals, we're going to choose a value to test and determine f prime of x at that value. Right. So we find the critical values, we set up a number line and put the critical values on it. And then we're going to check the intervals around those critical values to determine what the derivative is doing, okay? And that'll tell us what the function is doing. So if f prime is greater than 0 at that value, then f is increasing on the interval. And if the derivative is negative at the testing value that we chose, then the function is decreasing on the interval. So let's try it out. Find the intervals on which this function, f of x equals x squared minus 4x, is increasing and on which it is decreasing. So we're going to find the critical values first. So we're going to take the derivative, so f prime of x. So we take the derivative, that's 2x minus 4. And we want to determine any values that make this 0. So what we're going to do is we're going to set this equal to 0. And now solve for x. So that'll give us 2x equals 4. So x equals 2. Now we can set up our number line. And we'll put our critical value on there. And now we need to check values around that critical number and see what the derivative is doing at those values. So we can pick any values we want around 2 on either side. There's no necessarily any restriction on what we can choose or not in this case. You can pick numbers as far away from 2 as you want, but generally we want to pick the easiest numbers possible. So on the left over here, a lot of times if 0 is an option, that's a pretty good, easy choice. So we'll pick 0 and we'll check the derivative. That's 0 minus 4, so that's negative 4. So that's less than 0. So I'm going to put a negative symbol right there. And then I need to pick a number above 2, so I'll pick 3. So we'll check f prime of 3. That's 2 times 3 is 6, minus 4 is 2, which is a positive number. So I'm going to go ahead and put a plus right there. And as you can see, it doesn't even really matter that much what the number itself was. What really matters was whether it was positive or negative. And so then for myself, I like putting kind of just little guidelines here to make the graph a little clearer. So the negative means the function is decreasing. So I put a little decreasing section like that. And then the positive means that it's increasing, like that. So we have decreasing from negative infinity to 2 and increasing from 2 to infinity. I didn't include 2 in either of those intervals because technically at 2, the graph is perfectly horizontal. It's perfectly flat. So we don't include it because it's neither increasing nor decreasing at that point. This process that we've just described is called the first derivative test. So we use the first derivative test to determine relative extrema. So relative extrema being extreme values, so like maximum values and minimum values that are relative to their general vicinity. So we can say if f of x has a critical point at x equals c, then f has a relative maximum at c if the function is increasing on the left of c and decreasing on the right of c. So in other words, if the derivative f prime goes from positive to negative at c. So if the graph is going like this and then it starts dropping like that, that point up here is going to be a maximum. And on the flip side, we say f has a relative minimum at c if the function is decreasing on the left of c and increasing on the right of c. So in other words, f prime goes from negative to positive at c. So this case that we just described, that would be something like this. Right? Go from decreasing to increasing. So that would produce a relative minimum. Now, we call these relative maxima and minima because this doesn't necessarily mean that they are the highest possible value of the whole function or the lowest possible value of the whole function. What we're saying is in their immediate vicinity, so relative to the location where these values are, they are the highest thing around them or the lowest thing around them. But we're not saying that they are the highest or lowest of the entire function, right? So if we had something like, I don't know, something like that, right? You can see all of these points where we go decreasing to increasing to decreasing to increasing, decreasing, increasing, decreasing, increasing. So there's a ton of max and min values in here, right? And these are all relative extrema. But like if I show that there's a maximum here, this is higher than everything else around it right here in this vicinity, but it's not the highest thing on the function, right? All these values up here are higher than it. Okay, so we're looking for a relative maximum and minimum here. And an important thing to note about the first derivative test is just because f has a critical value at c does not mean that there is an extreme value there. Okay, so this is why we have the tests like this. So just because you have a critical point does not mean that it's a max or a min automatically. That's why we have to check it. So let's take a look at an example. Find the relative extrema for f of x equals x to the fourth minus 8x squared. So we're going to take the derivative. So that's going to be 4x cubed minus 16x. We're going to set that equal to 0 so that we can solve for any x values that make this graph flat. Let's see, we can factor out a 4x. We're left with x squared minus 4. So we get 4x, x plus 2, and x minus 2. So this is going to give us our critical values of -2, 0, and 2. All right, we get the -2 from here, the 0 from here, the 2 from here. So we set up our number line, and this time we've got 3 values. So we need to check values in the intervals around these. And again, they can be any values we want, but we want to try to make the values as easy as possible. So like down here, I'm going to try f prime of -3. I'll try f prime of -1, f prime of 1, and f prime of 3. Those are probably going to be the easiest choices. And we're going to check by plugging these back into the derivative. Okay, so plugging them back in to here. You can also plug them into like any version of the derivative, like if you wanted to plug them into here. Because all that really matters is whether they're positive or negative, right? So like with -3, for example, I know this will be negative, this will be negative, and this will be negative. Negative times negative times negative, that is negative still. So that means that's going to be a negative there. That's less than 0. Okay. And then we can do the same kind of thing. With -1, we get a negative, a positive, and a negative. Those negatives cancel, so that becomes a positive value. Okay, so that one's greater than 0. And then we can keep going. So with 1, we get positive, positive, negative, so less than 0. And with 3, it's all positive. So we go negative, positive. So our graph is going down, then up, then down, then up, like that. So decreasing, increasing, decreasing, increasing. So in terms of the relative max and min values, we're going to have minima here at -2 and 2, and a maximum at 0. So we're going to have a relative max. The x value is 0. If we plug that back in to the original to get the y value, we get out 0, 0. For the relative minima, if we plug in -2 back into the original again to get the y value, we end up getting -16. And if we plug in +2, we also get out -16. So those would be the relative extrema for this function. Okay, so we have 1 relative max and 2 relative mins. We can also tackle problems involving application to this topic as well. So a drug manufacturer produces a medicine whose concentration in the bloodstream is given by this function C of t, with t being in hours. After how many hours is the drug concentration in the bloodstream at a maximum? And then what is the maximum concentration? And then the question, what happens to the concentration as time keeps passing? We'll deal with that one after. Okay. So we're looking to find the maximum, right? And it's saying how many hours. So we're looking for a value of t, and it's asking what is the maximum concentration. So we're going to find the C of t value as well. So we need to take a derivative, which sometimes is easier said than done. This is a rational function. We need to employ the quotient rule in order to do this. So we're going to take low d high, so derivative of the top is 7, minus high d low, so that's 10t, all over low squared. So let's see what we get here. We have a 35t squared plus a 140 minus a 70t squared. So we end up with a negative 35t squared plus 140. Oops, square that, over the denominator squared, which we should go ahead and just leave. I think we talked about this when we did the quotient rule. It's better usually just to leave it as is. Don't try to expand it out. It's not really going to help much of anything. In terms of potential solutions, the denominator, you can get cases where the denominator makes the derivative undefined, which can potentially produce critical points, but that's not going to happen here because you have this value of t is being squared, so this number will always be non-negative, and then you add 20 and then you square that, so you're never going to get a 0 down here. So you're not going to get any solutions out of that denominator, but the numerator we can work with. So we're going to set that equal to 0. And if you move the t squared over, and divide both sides by 35. You get t squared equals 4. So t equals plus or minus 2. So we set up a number line. We check values around the 2's, so c prime of -3, c prime of 0, c prime of 3. Again, they can be anything, but pick easy ones. We end up getting, if we plug this into this version of the derivative, again, the denominator is always positive, so really all that matters is the value up here. But we end up with less than 0, greater than 0, less than 0. So we get negative, positive, negative. So the graph goes down, up, down, like that. Now, if you think about the context of this problem, they're administering the drug at time 0, presumably, right? That's when it first goes in. That's like hour number 0. So really, everything that happened before that is kind of irrelevant because of the context of the situation. But we can see either way that the maximum is occurring here at 2. So we know that the maximum concentration, it also asked us what the maximum concentration is. So we could do that. C of 2, that's 14 over 20 plus 20. So that's 14 over 40, 7 over 20, which we can convert to a decimal. That's 0.35. So 0.35. So maximum concentration of 0.35 after 2 hours. And then for part B, it's asking what happens to the concentration as time keeps passing. Intuitively, we should hopefully have an understanding of how this works. As time keeps passing, if they don't re-inject more of the medicine, right, it's going to eventually fade and get lower and lower and lower, right? There will be less and less of it as it gets absorbed. We can prove this by taking the limit as t goes to infinity, so as time goes on forever, of 7t over 5t squared plus 20. And then we can simplify this using some of our limiting tricks. So we multiply top and bottom by 1 over that highest power. So we get 7 over t and 5 plus 20 over t squared. So this is heading to 0. That's heading to 0. So this whole thing is heading to 0 over 5, which is 0. So we can say the concentration heads to 0. Which again should match what we would know intuitively as well. Now, everything that we've talked about up to this point has been dealing with relative extrema. So finding the maximum and minimum value in the immediate vicinity of these points. But we can also talk about what happens when you have an absolute extrema, an absolute extreme value. we say that f has an absolute maximum at the highest point on the graph, and f has an absolute minimum at the lowest point of the graph. Now, when we talked about the relative extrema, it was only the highest or lowest point of everything around it. When we talk about absolute extrema, we're talking about the highest and lowest point anywhere on the entire graph. And so there's an important kind of caveat here. A function does not have to contain absolute extrema. It is very possible, and it happens in many functions, that they do not have an absolute highest or an absolute lowest value. For different reasons, they can have like horizontal asymptotes. They can have vertical asymptotes, right? They can go off to infinity or negative infinity in both directions. They can have open-ended endpoints. So you can have lots of different cases where a function does not have an absolute max or min. I have a couple different graphs down here we can peek at. So like for this graph, notice this point up here has an output that is higher than anything else on the graph, right? So this point would be the absolute maximum for the graph. And then if you look at all the points on here, this graph does appear to be finite. And this point down here, this endpoint, does appear to be the lowest value, right? Lower than anything else. So that would be our absolute minimum. But now if you look over at the other graph, we have an open circle up here. So this endpoint is not included. And then it dips down, back up, and then down, and then it continues on forever in that direction. This graph has a couple of relative extrema. There's a relative minimum right here and a relative maximum right here. But there is no one single highest value because the function is approaching that point but never actually hitting it. And then the function is heading down towards negative infinity. So in this case, there are no absolute extrema on a graph like this. Okay. So let's take a look at an example with a pre-made graph. Determine any relative and absolute extrema for the function whose graph is given. Okay, so we're going to look for relative maxima, relative minima, absolute max, and absolute min. So let's see here. For relative maximum, we're looking at this point, right? It goes increasing to decreasing. And this point, increasing to decreasing, like that. So we're going to have the point 4, 4 and the point 8, 9. Then for relative min, we can't include this endpoint as a relative because in order for it to be relative, it would have to be decreasing then increasing. But because there's nothing on the left-hand side over here, we can't satisfy that definition. So we don't include that. It's just this one. It's just 6, 1 is our relative minimum. Absolute max, we look for the highest point on the whole function. That's right here. So that's also the 0.89. And that's okay. Points can be relative and absolute extrema at the same time. That's totally fine. You can even have multiple points sharing the title of absolute max or min. Like if this curve instead went up here, stopped here, and then came back down like that, these 2 points would both be absolute maxes because they would share the title. But that's not the case in this one. And then absolute min, it would be this one, except this graph continues on forever towards negative infinity. So there is none. There is no absolute min in this graph. Now, I've made a big deal the last few minutes about how a function does not have to contain an absolute max or an absolute min. There is one caveat to this, though. If f is a continuous function on a closed interval, then it must have absolute extrema. So this is the one kind of exception to that rule. If you know that the function is on a closed interval, okay, so it contains its own endpoints, and it doesn't have any like jumps or gaps or asymptotes or anything like that, then it must have an absolute max and an absolute min. So like on this graph that we're looking at right here, absolute max would be right about here, right? And then absolute min would be this endpoint down here. Okay, but having a closed interval guarantees that there will be an absolute max or min. Now, how do we find the absolute max or min? If we're given like a function, like a formula, we need to find any critical values, find any endpoints, okay, where the function is cut off, and we're going to check the outputs for all of those. And we're going to see what's the biggest and see what's the smallest. So let's take a look at an example of this. So find the absolute extrema for this function on the interval from -1/2 to 4. So we're going to find critical values and then determine endpoints. And then we're going to check their outputs. Okay. The highest output we get is the absolute max. The lowest output we get is the absolute min. Again, assuming that we're working on a closed interval. So let's try it with this one. F prime of x, we take the derivative, that's 3x squared minus 6x. We set it equal to 0, and we factor and solve, so that's going to be x minus 2. So we get x equals 0 and x equals 2. So these are our critical values, and we do have endpoints at -1/2 and at 4. Notice this is a closed interval because the endpoints are included. So we don't even need to do a number line on this one. We just need to get the outputs for each of these from the original function. Okay, so all of these come back from the original. So we're just plugging in to get their y values. If we do that, I'll spare you the time of punching all that in. We get these values. And now we just look at what is the highest output and what is the lowest output, and those are absolute extrema. Highest is here at 17, so that's 4 comma 17. And the lowest is -3 at 2, so 2 comma -3. And if you were curious, just as kind of a side note, it didn't ask us to determine relative extrema for this one, but in case you wanted to try it on your own. So actually the interval, we cut it off here. But we would end up with a positive, a negative, and a positive, like that. So we could find the relative max and mins if the problem had asked us for it, but it just didn't ask for it. So we didn't need to do that. But if you wanted to try it for practice, that's what you would get. And you could get those extrema as well. All right. But that brings us to the end of section 3.1. It's our introduction into the first derivative test, to relative and absolute extrema. When we come back in the next section, we're going to be looking at some additional tests, more things we can do to determine extreme values, and then continue through the rest of the chapter with applications. So I will talk to you all in the next one.